Good day, tourists. I am Kiana, your tour guide for today, and it's my pleasure to be service to all of you. Thank you. Before anything else, I want to discuss our rules and regulations here. When the tour guide is speaking, always pay attention and avoid talking to the person next to you. Eating are allowed, but be responsible to your ways. Always stay with the group, and if you have a clarification, want to clarify, don't hesitate to call my attention. Thank you. Is that clear, tourists? So if we are really clear, let's get ready for this tour. Tourists, welcome to our proudest museum, the Goddess Museum of Civil Engineers. So here's the map of our museum. As you can see in this map, we highlight the 3 galleries that we will be visiting now. While we on our way to the first gallery, please open your phones and check our Facebook page named The Goddess Museum and kindly like, follow, and share it. Thank you. Our first stop, the geometric design of highways. So the design of highways necessitates the determination of specific design elements which include the number of lanes, lane width, the median type and width, the length of acceleration and acceleration lanes for on and off ramps, need for track climbing lanes for steep grades, curve ready required for vehicle turning, and the alignment required to provide adequate stopping and passing sight distance. Many of these design elements are influenced by the performance characteristic of vehicles. The alignment of a highway is a 3-dimensional problem measured in X, Y, and Z coordinates. Here is the illustrated form from a driver's perspective. Since it has a consequence, the 3-dimensional highway alignment problem is reduced to 2-dimensional alignment problems. One of the alignment problems in this figure corresponds roughly to X and Z coordinate, and it referred to as horizontal alignment. The other corresponds to highway length and Y coordinate, and it is referred to as vertical alignment. Vertical alignment. It is the elevation of these roadway points is usually determined by the need to provide an acceptable level of driver safety, comfort, and proper drainage. It can also be broadly classified into crest vertical curves and sag vertical curves, and note that the distance from the PVC to the PVI is L/2. Here is the illustrated form of the crest vertical curves and the sag vertical curves together with the meaning of each term. We have here different types of vertical alignment. The vertical curve fundamentals, stopping sight distance, and crest vertical curve design, stopping sight distance and sag vertical curve design, passing sight distance and crest vertical curve design, and lastly, underpass sight distance and sag vertical curve design. Horizontal alignment. The critical aspect of this is the horizontal curve, with the focus on the design of the directional transition of the roadway in horizontal plane. Stated differently, a horizontal curve provides a transition between 2 straight sections of roadway. A key concern in this directional transition is the ability of the vehicle to negotiate a horizontal curve. As was the case with the straight-line vehicle performance characteristics, the highway engineer must design a horizontal alignment to accommodate the cornering capabilities of a variety of vehicles ranging from nimble sports cars to ponderous truck. We have here 3 types of horizontal alignment: the vehicle cornering, horizontal curve fundamentals, and the stopping sight distance and horizontal curve design. Now we're going to our second stop, which is the pavement design. Pavements are among the costliest items associated with highway construction and maintenance. These are the largely responsible for making the U.S. highway system the most expensive public works project undertaken by any society. So because of this, it is important for highway engineers to have a basic understanding of pavement design principles. In the United States, there are over 3 million miles of highways. About 45% of these roads are lower volume roads that are not paved. Highways that carry higher volumes of traffic with heavy axle loads require surface with asphalt or Portland cement concrete to provide for all-weather operations and prevent permanent deformation of the highway surface. So some states such as California, Illinois, New York, Pennsylvania, and Texas have a pavement construction, maintenance, and rehabilitation budget that easily exceed $1 billion per year. Fundamentally, a paved surface performs two basic functions. First, it helps to guide drivers by giving them a visual perspective of the horizontal and vertical alignment of the traveled path, thus giving drivers information relating to the driving task and the steering control of the vehicle. The second function of pavement is to support vehicle loads, and this second function is the focus of this chapter. In general, there are two types of pavement structures, the flexible pavements and the rigid pavements. As with any structure, the underlying soil must ultimately carry the load that is placed on it. The pavement's function is to distribute the traffic load stresses to the soil at a magnitude that will not shear or distort the soil. So in this chapter, attention is directed toward an accepted procedure that can be used to design pavement structures for a high traffic volume highway facilities subjected to heavy truck traffic. Traditional AASHTO flexible pavement design procedure. So there are several accepted flexible pavement design procedures available, including the Asphalt Institute method, the National Stone Association procedure, the Shell procedure, and the Mechanics Empirical Pavement Design Guide. Most of the procedures have been field verified and used by highway agencies for several years. A traditional and widely accepted flexible pavement design procedure is presented in the AASHTO Guide for Design of Pavement Structures. In this part, we have three important terms, which is the serviceability concept, flexible pavement design equation, and the structural number. Measuring pavement quality and performance. So the design procedure for pavements originally focused on the Pavement Serviceability Index as a measure of pavement quality. Efforts have been undertaken to develop quantitative measures of pavement condition that provide additional insight into pavement quality and performance and that correlate with the traditional Pavement Serviceability Index. Some factors that are regularly measured by Highway Pavement Agency now include International Roughness Index, friction measurement, rut depth, cracking, faulting, and the punch-outs. Finally, we are here to the last step, which is the traffic engineering. Road traffic signs. The importance of road signs have been recognized worldwide because of the increasing incidence of road accidents due to the volume of traffic and bad habits of motor vehicle drivers. Here is the following objectives of the road signs. Visibility and legibility of road signs or the pavement markings are dependent on three parameters: the detection, identification, and the reading. Road signs are classified into the following categories: danger warning signs, intersection signs, prescription signs, general information signs, direction signs, agglomeration signs, railway crossing signs, temporary signs, and the special instruction signs. Highway capacity and level of service. So the capacity of any element of the highway system is the maximum number of vehicles with reasonable expectation of passing over the section during the given time period under prevailing roadway and traffic condition. Here are the defining terms associated with capacity: maximum volume, number of vehicles, reasonable expectations, one direction against two direction, and a given time of period. So I guess this is the end of our tour. I hope you learned something from the galleries that we visited, and also hoping that you're satisfied and enjoyed this tour. I'm looking forward now for your feedbacks on our Facebook page. And that's it. Thank you and have a nice day.